Hello everyone, and welcome to the Force of Kinetic Friction pre-lab. What we want to do today is basically what we did a long time ago to the force of gravity. Right? We've been putting, we put the force of gravity on many of our system schema and our force diagrams, but eventually we broke it down into something more fundamental. We figured out that near the surface of the Earth, we could calculate a force of gravity by taking the mass times the gravitational field strength, right? mg, where near the surface of the Earth, g is 9.8 newtons per kilogram. And that way we could kind of work a little more fundamentally with what was going on. So we've talked about friction being something that resists motion when surfaces rub against one another, right? Acts parallel to the surface and opposes the motion. But now we're going to try to break it down into something a little more fundamental. So what do you think might affect how much friction there is between two surfaces that are rubbing against one another? Well, a lot of times people will say at this point, well, what about the mass of the object? And I'll say, okay, but why? And they'll say, well, because then there's more gravity. Okay, so how is that going to affect friction? Well, that'll push it against the surface more. Oh, okay. But gravity is an interaction between the entire Earth and the object. What force is it that talks about the force between the surface and the object? Because isn't that the one that would lead to friction? Right? And that is the normal force. So instead of using gravity here, we need to use normal force. Right? As you know, sometimes the normal force is equal to gravity, like in horizontal cases where all the forces are either horizontal or vertical, nothing at an angle. But sometimes the normal force is more complex, right? And it might depend on the angle that it's at or other forces that are happening. Right? So normal force is what we want here because it's the force between the surfaces. The other thing is what kind of surfaces you have. You naturally know that some surfaces, because they're rougher, have more friction than smoother surfaces. Now, there's sometimes other things that people will come up with, but not that we're able to test in our lab. So we're going to stick with these three variables. And here's the device that we're going to use in our lab. It's fairly complex, okay? You might remember these constant velocity cars, okay, that we used back in the toy car lab. I didn't really draw the diagram perfect, but this on here represents the other car, the fancy cars we've used recently with the force probe. Right? So we're going to have that, and it sits on top of it, and it fits perfectly together, as you'll see. Little block of wood in between, with a little hook on the end, right, to which we will attach a string, and the string will be attached to these two things. These are called friction trays. You can open them up, and they're empty inside, so you can put things inside of them. You can hook them back together. Notice how the string here is horizontal, and it's attached to the top tray. Not the bottom tray, but to the top tray to keep everything nice and horizontal. Right? Remember that these force probes are unidimensional, so you can only pull on them in the direction that they're oriented, not in an angle. You won't get a true reading out of them. And when you hit the button over here, flip the switch, this is what it's going to look like. And notice, how is it moving? Constantly. Right? It's not accelerating. It is moving at constant velocity. Remember, that was the whole point of using these cars back in the toy car lab, was to identify what constant velocity looked like. Right, so it's going to pull it at constant velocity. Everybody with me there? Fairly complex little setup, but works really well. Well, works reasonably well. Friction's kind of a hard animal to deal with. So let's talk about what's going on with these friction trays. And by going on, I mean, what are the forces involved here? Well, of course, they weigh something, so there'll be a force of gravity acting on them down. You're going to have these riding on a little track, right? Your track that you've put carts on before. So the track is definitely supporting them, so there'll be an upward normal force. How big will that normal force be compared to gravity? Well, what kind of motion is it? Constant velocity, zero acceleration, and anyway, it's not really moving at all vertically, so those forces will balance. Okay, the normal force is equal to the force of gravity in size, in magnitude. That means if we want to know how much normal force there is, We just have to calculate the force of gravity. And we know how to calculate the force of gravity. Right? It's mass in kilograms, got to be in kilograms, times the gravitational field strength, which near the surface of the Earth is our old friend 9.8 newtons per kilogram. Right? So whatever mass we put in here, whatever mass these are, right, we can figure out the normal force, the support force, the contact force between the track and the trays, right, by calculating the force of gravity. Now, if you notice here in the picture, there's also a string attached to the front end. So that's a force of tension. And then, of course, the whole point is that we are sliding these trays over the track, which means there'll be a force of friction, which always acts parallel to the surfaces and opposes the motion. So it will act to the left. Well, how much friction will there be? Since it's moving at a constant velocity, zero acceleration, those forces have to balance. So if we want to know how much friction there is, we just need to figure out how much tension there is. But how can we figure out how much tension? Because the string is attached to a force probe. And the force probe will make a graph for us so that we can see the force of tension. I'm going to show you in a little bit what that graph will look like. So this is a little weird of a lab. We're not actually measuring things directly. Okay, our force of friction and our normal force, we're measuring them based on other forces that we can measure or calculate, and given a special situation where we are pulling these trays at constant velocity, hence zero acceleration, so that all the forces have to balance according to Newton's first law. So we're going to figure out the force of friction by relating it to the force of tension, which we're just reading on the force probe. And we're going to calculate the normal force by calculating the force of gravity, which is mg. Types of surfaces, well, I'm going to kind of break this down so that it doesn't take us too long to do this lab. Half of the room is going to use a tray that has cork on the bottom. So there'll be half of the room will use cork on track. Right? That'll be your surfaces. The other half of the room is going to have a tray on the bottom that has plastic. And so it'll be plastic on the track. And we're going to compare what you get and see what effect the types of surfaces had on the force of friction as well. Okay? So our purpose here is to create graphical and mathematical representations of the relationship between the force of friction, the normal force, and the types of surfaces. Now, can we control the normal force? Well, remember, the normal force is equal to the weight, and yeah, we can control the weight by controlling the mass. So if we open up this friction tray and put masses inside of it, we change the mass, we change the weight, we change the normal force. So the normal force will be an independent variable. The way you're going to do this lab, as you'll see on your lab sheet, is you're going to start out with just the two friction trays, and then you're going to add 100 grams at a time into the friction trays for each additional set, each additional trial. Okay? Now be careful. The mass you need to calculate the weight, to calculate the normal force, is the total mass of both trays plus anything you put inside. Okay, so be careful when looking at the lab sheet, all right? I tried to show you that with a couple of different columns. Okay? Now we are making an estimation of what these two trays are. And by the way, the cork bottom tray is pretty much the same mass as the plastic bottom tray. There's a little bit of error in that, but not a ton. Okay? And then the types of surfaces, like we said, half the group is going to do, or half the tables are going to do cork, half the tables will do plastic, and we will compare, right, the different types of surfaces and see if and how that affects the force of friction. That makes our force of friction the dependent variable. So when it comes time to making graphs, you'll be making graphs of force of friction versus normal force. Right? Force of friction on the vertical axis, normal force on the horizontal axis. One thing you do have to do with these force probes, remember, and you've seen this in the last few times you've used them, please zero this force probe. Right? Lots. All right? You have to disconnect the string from the force probe because you can't have anything pulling on it, right? And then you can zero the force probe. By the way, there's a sheet on your table and also on the schedule schedule docs that will allow you to connect your force probe to the computer and set up everything, get the force time graph, all of that kind of stuff, right? As you had to do in other labs. Follow the steps carefully, follow them completely, including the zeroing of the force probes. So here is a trial. It's not exactly the way yours is going to look, okay, but it's close enough, right, to what's going to go on here. Here we start out, and this is, by the way, a graph of force versus time, but remember, this is the force of tension, which is equal to the force of friction, so this is really a graph of friction versus time. So notice when you start out here, we're not getting any friction. And that's because, hopefully somebody hits collect and then you flip the switch. So until it starts. Plus you might want to leave a little slack in the string when you start out. Right? If you leave a little slack, it'll take a minute for it to start pulling. Right? And until it does, it's going to read 0. And then what's happening here with this spike that we see? And by the way, one of the things that's different about this graph that I pulled off of a website is that there's no way your spike is going to take 2 seconds to do. Your spike will take a fraction of a second. It'll be a very steep little spike with a sharp corner at the top. Right? But what's going on there? Well, what's going on there is that it's pulling, but it's not enough to actually make it start moving yet, right? You can pull on something and it doesn't move because there's static friction balancing things out. So it pulls harder, and it pulls harder, and it pulls harder until you get to the top point. And as it says here on the graph, that top point is the maximum amount of static friction. And then once it breaks it free and it starts moving, it's going to drop down to a basically constant amount of kinetic friction. Now you'll notice here, this is not going to be a perfectly horizontal line as it would be ideally. Okay, it's going to bounce around a bit, and it might even bounce around more than this. We're taking lots of data points, many a second, so you're going to see some bouncing. Now, why is it bouncing? Well, it's bouncing around because of something mostly called slipstick, which means that the tray is alternately slipping and sticking to the track, and so that slipstick makes it kind of oscillate a little bit here. Needs a little more force, a little less force, a little more force, a little less force. So what force are we going to use? Well, we're going to kind of do this like we did a couple of labs ago. You're going to select the horizontal part, right? Not up here, not when it's spiking, not before the spike, but after. Select the horizontal part, go down to the bottom and do statistics, and then you're going to take the average, the mean. All right, so you're really going to you'll notice on your lab sheet, you're only doing one trial of each normal force. And that's why, because you're going to average dozens, maybe even hundreds of points together, depending on how yours works. Okay? So, again, you're going to select the horizontal part, right? And get an average force, kinetic friction force. So we've got no force, static friction, which notice has a range of values until you pull hard enough to break it free. Now, one other thing I want you to notice about this graph, and you'll see this in every one of your trials, the maximum amount of static friction is greater than the kinetic friction. This is an experimental proof of something which I hope you've pushed things around enough to notice. Is it harder to get something going or to keep it going once you've got it going? Hopefully you'll agree with me that it's usually harder to get something going, right? But then once you get it sliding, it's easier to keep it sliding. And this is showing you that experimentally. Static friction, range of values, but it has a maximum, and that maximum amount is more than the kinetic friction. Kinetic friction, there's only one value. Static friction, there's a range of values. And after this lab, there's going to be a movie talking about some static friction. Okay? So pretty clear on how you're going to use that, right? Ask questions. If you're confused, there's all sorts of things on the lab sheet and the setup sheet. And of course, there's always, when you make your own graph, the graphical analysis, data analysis with graphical analysis sheet, all linked in the schedule doc.